Okay, so everybody, welcome to binarysearch.com. Today we have weekly contest 40. We'll start any second now. So I guess, yeah, let me make myself a bit bigger. I guess we'll try to solve everything, but let's see how it goes. I'm kind of new to this platform, so let's give it a try and have a lot of fun, of course. Contest will start shortly, whatever that means. Okay. Okay, we can wait, we can wait. We are not in a hurry, right? Is it going like to refresh the page, or what's going to happen? I don't know. Like it's my first time on writing like an actual contest here. As you can see at the top, I started to. No, you can't see because my image cover stopped. But I started a bit of preparation today just to get familiar with the platform. Should I refresh or what? What exactly I should do? I'm not sure. Hello, let me in. Let me in. Yeah, obviously refreshing was a bad idea when you have a not perfect internet connection. Am I? What am I supposed to do? Like, what if I just try to go or what's going on? Well, that's obviously not the perfect start to the contest. Okay. What I'm supposed to do? It's not. Is it my internet or it's not? Well, apparently I have an adequate internet connection, right? Yes, we have my mail. Okay, then it's a platform. Oh, okay, okay. Well, we have like entire hour to solve about 4 questions, I think. So it should not be like very difficult, right? Maybe server load is actually huge, or maybe just so it takes a lot of time to just get going. Well, either way, we're not spending all that much time, right? Okay. Unobstructed buildings. Honestly, I first read it like unstructured buildings, but okay. We're given a list of heights, represented building heights, so we have some sort of skyline. The building can see ocean, and every building of its right has smaller height, okay. In ascending order, okay, so I guess we just have to go from right to left. And check who is visible, and also maintain track of highest so far. So initially highest so far, I guess integers are integers positive. I mean, they should be. But okay, but let's start with origin. So we're going from right to left. Original, the highest building is at -1, so there's no buildings, just to make sure that we don't have like buildings of height 0. Every time we encounter a higher building, we have to update the index of highest building so far, height of the highest building so far, and also append it to visible. So let's go. And I think that we have enough time to write reasonable code. So I will go with reasonable variable names for Building index gets, so we iterate from right to left, which corresponds to decreasing indices, right? Uh, okay. And we have to check if heights building index is greater than actually, yeah, smaller. So we, if it's strictly greater than visible building indices, and we would like to push back our current building index, and we would also like to update the highest so far. I believe highest so far is high. What's the span of highest? Let me check. Oh, actually, I was correct. Well, okay, so we want to update the highest so far. Very good. And I believe we want to also reverse visible building indices just because, or actually, you know what? I suppose that we can construct, yeah, I did not name a type. Okay. I suppose we can construct a vector from two iterators, but apparently I was wrong. So never mind. Uh, I thought that it's going like to cast basically. Let's check if this works. 2,4 is correct. Yeah, I don't necessarily like how we have to copy each test case by itself. And also something really bad happens because we are stuck. We are officially stuck. Oh, I don't know. Can we? Oh, we can't submit when it's running. Well, I guess we don't have anything but to wait. Okay, that's correct. Is this correct? Yes, it is. So let's try. I think it's okay. How do we get to the next problem? I don't understand. Oh, okay, there's an arrow. Number of moves to capture the king. So we have some checkboard. I think two-dimensional integer matrix board. Okay, 0, 1, 2, 0 empty, 1 knight, and 2 king. There's at least one knight, but exactly one king. Given the king stays still, returns minimum number of moves to take some knight to land on the king. Okay, okay. You know what I'm actually thinking? Like I believe there is a mathematical formula for the distance in knight moves between two cells of a matrix. But what we can do is also multi-source BFS because we have not all that many vertices. So let's do just this. Okay. So we will need a deck here of integers, which will be, of course, BFS. And we start, well, yeah, we start at every knight. And we will also need some helper, vertex ID. We give it row, we give it column, we give it, oh, it's also squared, but we'll give it column count, it will return. Also can be made in line to save some time. So it will be a row times column count plus column, which basically means that we enumerate all the cells from a left top, so row by row, inside rows, column by column from left to right. Reasonable, right? Let's check if this is what we want. I think so. In board, we will need a board size, of course. I think board is square, which is convenient, very, very convenient. Okay. Then we're just going to iterate over all rows and copy paste the same, or actually, or iterate over all columns. Okay. If row, no, if board at row column is equal to 1 destination, we will need a destination. Yeah, well, let's originally set it to -1, but we don't, it will always get the correct value here. Gets what? Vertex ID of row, column, and board size. Else, if it is 2, don't necessarily need to write else, right? These statements are obviously disjoint. Nothing ends up in the two statements, but it's okay. I like it more the way it is. We are 100% sure that when reading the code, we are 100% sure that we won't end up into different branches. I find it quite helpful because when you have like multiple if statements that are disjoint, but you don't see it from the code, and you can get lost in this code. I don't like being lost in my code, so let's be explicit as possible. Okay, now we filled in our BFS. I guess we will need some sort of a distance. Board size times board size, numeric limits int max. Also distance. I'll need this separated. No, actually ID, right? Oh, we can't define, okay. It's going to be a vertex ID shortened because I can't define the set. Actually, that was a mistake because I didn't follow the correct case rules, right? So don't be like me. Now we can use a great name, vertex ID, like so. Then while not BFS queue is empty, we take the BFS size. Because we are going to do like one iteration, we take all the vertices from BFS out and process them at the same time, so to speak. Or actually, I'm not sure that we need this. I don't think that we need it, right? Yeah, I don't think we need it because we have a distances nearby. Okay, so we take one vertex out. It is BFS front, I suppose. And we remove it from the queue, and let's think what goes on. We want, actually that's not very nice, but it's bearable. So what I need, in fact, is reverse transform, right? So rows will be vertex ID divided by column count, and yeah, because I want now to get like current row and current column from our vertex ID, but because now we will need to iterate over adjacent squares. And what are adjacent squares? It is, of course, like plus 2 or minus 2 in one direction, and then plus or minus 1 in the other direction. So let's do just this. Row delta equals minus 2. Actually, yeah, I'm a bit lazy, so I'm going to do with the following. Like if row minus 2 is at least 0 and row minus. Oh, you don't need to check against the upper bound when you subtract. Yeah, if so and so, then after adjacent. So we are basically computing the ID of the adjacent vertex. And here we also want board size, I guess. So let's go here. Now we have the ID of adjacent vertex. And we also want to add a bunch of these. So first of all, the interchanged one, go -1, -2. And the one where we go -2 plus 1, right? Doesn't board size, I guess. And the one where we go -1 but +2. -1 +2 here for us. Also here we have, then we will need to add actually to row. So why don't we just copy paste this? I know it's not the most efficient way. You probably can enumerate them just much easier. But whatever. I guess it works. Like want to compare to board size all the time. Okay. Now, if distance to adjacent ID is smaller, or actually greater than a distance to current vertex, so that's vertex ID +1, then you want to then you want to update basically, right? Just like so. I think it can be like written in a faster way. You just take the minimum of 2, right? That way you don't need an extra if statement. Okay. And I think we have to do it all the time, and that's unfortunate. I believe it would be much easier if we looked through these increments in some sort of smart way. Let's maybe try it, right. Delta row, or should I say row delta, equals -2. Row delta is at most 2 plus row delta. Let's check the same for column delta. So first we want to check that row plus row delta is at least 0, because delta can be negative. And we also want to check that it's at most board size. Then we want to check that column plus column delta is at least 0, and also that it's at most board size. Very good. Then we can, it's not done, it's not done. We need to check also that this is indeed how the knight moves, right? So here we need more conditions, but this loop I believe can be like so much more better. It gets, right? At the end of if loop, it should be here. Should be here. Okay. I think this is it, and we can return a distance to distance to. No, it's not inside of BFS. Right? And we would also like to insert it into BFS, right? No, just push back JSON to the. No, actually, that's why we needed it. That's why we needed if statement. If this vertex, if this distance is bigger than this, then we assign, and only then we want to go to this vertex in BFS. And we also need to check some conditions. So I believe that you can check that knight move is correct by saying that absolute value of the product is 2. I guess so. I guess so. We can actually make this like first condition because it's the most important. I'm not sure if this works. It was a lot of code. Okay, compile error, but it's not terrible. Line 45. Yeah, right. Destination. Is it? Whoa, like actually. Actually. We'll need to return, like it can stay unreachable, right? So if it's equal, and we want to return -1, else we want to return the distance. Yeah, and we obviously spending a lot of time. Let's see. Okay. Okay, something did not work. I'm really interested why it did not work though. Can we actually print like a current vertex ID that we consider in our BFS? Oh, right. Oh, you can't move lines. I mean, you have to cut them and paste them back. Have some output. It was at some vertices. Oh, right. Because 1 is the knight and 2 is the king. Okay, accepted here. I guess there is no better way to copy it. Here we should get -1, but we get 0. Because I mistyped it, it should be 2 here. -1. Okay, let's try. I mean, BFS runs in linear time, should get accepted, but not particularly fast. Okay. Okay. Recursive voting. So we have a list of integer voters representing election voters for candidates A and B, and each element is represented to one of two candidates. If it's negative, then it's for first. If it's at list N, then it's for B. Otherwise, otherwise it's recursive. Okay. I guess we just can process them. I mean, every time we encounter the value sending us back, we will just update the current value to the correct count. Okay. So we want to output what? Okay, so we want to output A. Okay, so what count? Let's put it 0. We also conveniently can change volts. Okay. For auto volts in volts, watt smaller than 0, then watt count. I also think that we should 100% use long integers here. Okay, so it's negatives, then we decrement. Else if watt smaller than int lamp, okay. What's the size? So we will just you see, each city can either give us a correct number or send us back. But so the problem is that we potentially can, at the end of the range, we may encounter the situation where we need to go back a lot of times, like 100,000 times. We won't do that because every time we send back, we will update the current value to the correct number, so that next time when we get sent back, we already know it. So we do at most one go back operation. Right? If it's smaller than length, then we vote. Actually, we'll need to iterate with reference. Votes. Are we guaranteed that it gets back, or are we not? Oh, apparently we are not guaranteed that it goes back. Right, like this may go to second entry. Oh. Whoa, that's not great. Well, that's not great. Okay. I guess there is no better way to do it than to do it like that. And you'll see in a second. So I thought that we can just go, if we are only send back, then it's not particularly difficult. Let's see. So this DFS will find, actually it's not DFS because we only follow the path, but it will find the value at the end of the path and effectively update all the values, okay? So we have like what? If what's E is smaller than 0, then we indeed can update, pardon my parentheses, broken. If it's already negative, we can just update it. If it's smaller than 11, then we want to DFS and we want to what count to, because DFS will change some values in votes We will also return the correct value. Okay. So E and votes and return votes count. And what goes in O? It's an old habit of saving my files because I mostly I write like not in the online editor. Okay. So yeah, in parent is votes, or actually, let's see, if votes at vertex is smaller. No, actually, we don't want it. What we want instead is like this. Now, this is a situation when we want this to be not connected by else if. So if the vote is not defined, then we define it and then we check if we should count it. Also, because yeah, we will pass it's another variable. I mean, we obviously can deduce it from votes, but I don't want to. Okay, so if in this case it's already defined, right? So we will just return votes vertex. Else votes at vertex will get DFS from votes at vertex, votes, and len. So we every time we ask to go somewhere, we go there, but then we remember the answer. Because we have at most n edges in our graph, it will work in linear time. I think it should. It absolutely should. Okay, we have some compile error because we want to return the result of this assignment. Oh, but no, actually, we would like to do it again like this. So if this condition means exactly that our value is undefined, we only, and then we, yeah, it's a bit nicer. It's still accepted. Let's try. I don't know. Okay. Okay. My result is 10 because we have this 10. Oh, because 0 also means that we have to go and check. Yeah, yeah. Not paying attention to plus minus 1, you know, people. Not great, not great. Still something's wrong. Why is actually... Wait, what? Wait, it's less than 0. It votes for A. What is going on? What is going on? Why exactly is expected answer 0? Is 1. Actually, I don't understand. I don't understand. Where can I ask a question? Why it's not 10? It should be like 100% 10. Look at this. If votes is less than 0, then it's 1 vote. Whoa, whoa. Damn, I did not realize. I thought it's number of voters. And this case doesn't help in understanding whatsoever. Terrible people. Okay. We're given two-dimensional lists of integers matrix. Yeah, very good. I don't care about XP when it's a contest. Okay, don't show me notifications, please. We're given two-dimensional list of integers matrix. We want to pick a number from each row. The cost of picking and Okay, so we pay the change in columns between the numbers we pick. Okay, and we want to. Okay, so we want to maximize sum of numbers, and we deduce the cost, obviously. Okay. I actually think from each row. Okay. How many rows and columns do we have? We have. Okay, it's not particularly great. No, actually, now that it's not good, not good, not good. I mean, my idea was to do some kind of dynamic programming from row to row and see what's the best way we can get, right? So it's okay to have dynamic programming denoting like the most value we can get ending at that vertex. But then we have like quadratic number of moves between layers, right? And that's not good because we also have a linear number of layers, so it should not work. Like if we knew that these params, like each of them was at most 100, then it's a go. Currently, it's not a go. What I'm thinking is that when we iterate over one row, each element is the best ancestor for some segment, okay? If we can like quickly process this knowledge, then we may get away with a linear number of transitions between the two of them. Right, but how do we do it exactly? Like we have some numbers, each of them is the best ancestor for some interval. So each of them should be added to some interval. How do we know what interval is that? Now the problem is we can't go like only one way, right? Because then we may miss someone from the future. Oh, okay. I think we are done. Okay, we will just need two-way pass. Okay. And we also need to speed up a little bit, but not much. So no worries. Matrix size, I guess. Matrix 0 size. Are we guaranteed? Yes, all both numbers are at least 1. Original everything is 0. Int call equals 0. So we now want to initialize first row. dp0 call gets a matrix at 0 call. And then I guess we can return max element of the last row of our dynamic programming, because it will contain answers. Here we will make transitions from row to row plus one. That's why we also need to add this condition. Okay. I need to think for a little bit. I feel like we can do something as follows. Initial best call is 0. Then we think like the current number have to update the current cell. Otherwise, it's now gone. So what is the best value we get from best call? dp at row plus one call gets dp at row best call, right? Plus, what does it get? What does it get? Minus actually. Oh, okay, plus matrix row plus one call. So we travel from row best call to row plus one call, and we have to subtract obviously call minus best call. And I think like it's always non negative, so we can just go like that. But let's add it just in case. Okay. We try with best call, right? Otherwise, we can also try this current column. So if dp row call plus matrix at row plus one call plus 0, right? If it's better than the current value, then we have to update this and also update this. And now we also need the same thing in reverse. So I guess we go like that. This time best call has to be set to call count -1. I'm not sure if this actually works, but it's a reasonable approach. Okay, passes first test case. It's better than nothing. Is it valid? Okay. Okay, it makes sense to me. Oh, we obviously forgot about. Wait a second. Wait a second. Why would we do that, though? I mean, okay, and I also think that numbers can be quite huge. So to make sure we don't overflow anywhere, I really don't want to overflow. Okay. Let's also print our DP because apparently we had some failing test cases. I'm not sure whether it's a wrong algorithm or I just missed something minor in the implementation. Okay. Don't want to copy. Yeah. Here we can copy. Oh, we don't have to separate test cases. Okay. Output 0, -2, -3, -2. But wait, like here we could go from 0 here. Wait. Like here we go from column, which is 0, to this cell, and we go to this cell, right? I want to understand what transitions are we trying to make. So a row a space from best column, we are trying to go to column, right? Can we comment it somehow? Yes. Okay. Okay. We try to go in as first column from 0 to 0, from 0 to 1. We actually tried going from 0 to 1. But then what's the problem? Like this is 0. This is 0. This is -1. I don't understand. I don't understand, people. Okay. It's okay. We still have like a lot of time. Oh, because here we always assign. So if this is worse than this, then we have to assign. Otherwise, for frankly speaking, we don't have to do anything. Also, our code is getting not great. And I'm guessing that the solution is to int distance or I don't know, what is it? Score better than that. Go and update with score. Otherwise, we don't have to change it, all right? We also can make it a little bit more consistent by putting it like so. And again, if this condition stays the same, all right? Our result is 0, which is incorrect. Oh, because originally we have all zeros and we don't want to override them. That's correct. Let's set -infinity everywhere. And we also set in like first row correct, so it should be correct. No, why no? What's the state of our DP? 0 - 2, 0. No, you can't get like 0. You have to use it. You have to use it. I don't understand. Okay, we're trying to make all transitions possible. Then we generate our, oh, this is not correct. Now we are talking. Let's check me if previous test cases work, just not to waste too many submissions. I'm not sure if there's a penalty, but it's always nice not to have penalty. Okay. No, interesting. So I somehow got away with 1, but correct answer is 2. If you go from here to here. I'm not sure how it happened. I believe that when going back, we should have updated like from this one to this 2. Because this sum is like -1 and this sum is 2. Potentially here, no, here, this index was better, was clearly better. Okay, maybe, just maybe, we need to separate vectors. Oh my. Right, we need to separate indices. I think so. Let me grab this. Need to separate DPs because it's like oh, here we want to put it into DP row, okay? Then we want to take max. That will be correct because these two don't, they must not interact. Let's put it this way. Now we can look from column like so. DP row +1 column. It's max of row DP row +1 column and DP row. Is this any better now? We don't have to get rid of this. Okay, now it seems better. We also have some DP, which we can check. Let's again test on provided samples. Okay, so far, we're solving more and more test cases. Let's see if it works. Okay, now it actually works. Very good. Okay, well, we solved everything, right? There's no. Okay. Let me make a quick explanation, if so. Like in first problem, you have some sort of skyline, right? Like over this way, there's an ocean and people are allowed to see the ocean. So potentially that's why we are interested in from which buildings we can see it. So obviously we can always see it from the first building. Then we maintain two things. Can I, how do I pin? There was a button to pin. Okay. We also maintain like the highest we've seen so far. If we see anything higher, it means that we also take this. If we see anything that's lower than current max, then we can't see because we stare into the building. And if we again see something that's higher than that, then we again can't see over this building. And we also update the max height every time we encounter the higher building. That's first question. Let me go to the second one. So in second one, there is a board, right? Not like that, not like that. Okay, there's a board. And basically what we do, we say like, oh, it's a graph, right? we want to move using a knight to a king. Now we do this as follows. We say like we have a board. So cells of the board are essentially vertices of a graph, and we have edges that go like this. So a knight move edges, right? From here we can go somewhere here. From here we can go somewhere here, and potentially there's a king which we want to hunt down. So we have a total of 500 squared vertices, which is around 25,000. We also have 8 edges outgoing from each vertex. So that's 200,000 K edges. These are pretty natural constraints for a graph. So we can just do BFS, right? But we need multi-source BFS because we can have multiple knights. We have multiple knights and only one king. So potential like this guy over here can reach the king in 2 moves, but this guy can reach actually in 1 move, right? So we do multi-source BFS, or yeah, let me remove everything. So we have like the 25,000 vertices, 200,000 edges, and then we look. Like originally there are some knights, like let's say there are 2 knights, then we compute the distances. Like here we can go in 1 move, 1 move, 1 move, 1 move, 1 move, 1 move, 1, 1. From here we can go here, 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 here. And from each one we go again. Like from this vertex, for example, we can go here, from this here, 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 here. And like so, eventually we'll visit all the board, or maybe, let me finish and you'll see why I say maybe. Like so. I bet I'm missing some parts. Check, because we can go like here. So we can go from this one here and here. And as you may see, like board is pretty quickly filling up. There are reasons for that. And I guess we are done with 2. So as such, board will fill up, except several cases, which you can do by hand, but it's much easier just to use like BFS can check whether a vertex is non-reachable, right? So one example of non-reachable is, of course, 2x2 board. You can't go anywhere. The other example is 3x3 board. If the king stands in the middle, there's no way to reach it. You can go how many times you want, you will never reach it. And also in 4x4 board, there are some more than one connected components, I believe. So let's see. Let me actually draw like that and also like that, so I can fill it up. So if you start like here, then you can go here, 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 and that's it. You are stuck. If you, however, draw the board properly, right? Then you can you get another connected component, and you have more of these like this and like this. Yeah, starting from 5x5 board, I believe there's one connected component, so you can always reach the king, but I'm not sure. Also, I'm almost certain that there's like a big O of 1, it's a constant time complexity algorithm for finding distance between 2 arbitrarily cells of a checkboard. So you don't have to write BFS, but I was unable to sync. Yeah, syncing is not my strong side. Sometimes I just think that, oh, that code works, so let's write it. Like, okay. So yeah. So you just implement BFS over board multi-source because you have multiple knights. Then you have recursive voting. Recursive voting, it's pretty simple. So you can have some people redirecting to other people. You think like, oh, what's going on? Well, what we do is like we iterate over vertices. So this vertex does not send us anywhere. So we know how it votes. When say like this, we know how it votes. This don't know. So we go into recursive DFS, we get there, and eventually this vertex, yeah, let me draw like this. So we go there, and this vertex says, I don't know either. I will vote as my friend votes. And we go to this friend, and this friend says, like, for example, I vote for B, right? So here, for example, we had a couple of A's. Here we have a vote for B. We store these guys in a stack, in implicit recursive stack. So whenever this answers, we know who asked for this vote. Okay, so we go here, change this value to B, which efficiently erases this arrow. So what we did is this person said, I'm gonna vote as my friend votes. We asked him, oh, well, who is your friend? We get to this friend's home with only good intentions in mind, nothing about falsifying elections, of course. And then we said like, oh, we came back to that person. We said like, oh, your friend is going to vote for B. He says, oh, and I'm going for vote for B. And we also get back. So all vertices on this path are now decided, right? However, like we can have like edges going back and forth. Potentially, there's someone ahead who will vote the same as this person, but because we already determined its vote, we erase the arrow, so we don't follow any error twice, right? Once we determine its vote, the arrow is gone, and when we get to that pre-last person who says, I'm going to vote as this person, we already know how this person voted. Okay, so the key here is to overwrite votes as we go. Okay. Then we have a dynamic programming problem. Yeah, contest is finished. I guess we will wait. Yeah, I will just end recording editorial, I guess, and then I'll get back to the chat room so that you can ask probably some questions. But keep in mind that this video will come out like half an hour later because it needs processing, for sure. So in this problem, we have a matrix of numbers. There are some fees. So we want to traverse it from top to bottom, get maximum sum, but there are some fees to go from. So like you can't just randomly switch from left to right. You have to more or less stick to the same path, because the more you go to the side, the more you pay for going to the side. Now going straight is much easier than going in diagonals. You have numbers like this. What I essentially say, like, well, let me for each number compute the dynamic programming, which will be like what is the best path ending here? Well, that's this path, right? Essentially not the path but the sum, because we don't care about the past path, right? Then I say like what's interesting about this problem is that every number here is a best parent for some subsegments. For example, here 3 is the best parent for 4, and 6 is the best parent for anything else, right? Well, because, yeah, that's not a perfect example because it's not particularly interesting. Let's assume there's also 5, 1, I don't know, or 4, 1, 2, 3. So here, 3 is the best parent for these two guys, and 6 is the best parent for everything else. Now, because of the way it works, so if, for example, if you take a look at this number, if 3 is better parent than 2 for this number, then 3 is also better parent than 2 for the next number, because both of them will have to pay one more from what they paid to get here to get there. So the relative cost doesn't change. That's why each vertex, each number is the best parent for some interval. And you can use it to solve the problem as follows. Yeah, let me finish our example. Here, 4 will be the best parent for this region, I believe, and for the rest of them, 5 will be the best parent. Yeah, so how to compute these best parents? Well, initially you say like, oh, for this best parent is for every number is either here from the left or from the right. We will do 2 passes to determine what's the case. So first we check like what is the best parent on the left, including this number. Let's start like, oh, well, our initial guess, we don't know anything about the problem. So our initial guess is the best parent for 2 is the one above it, because it has the lowest fee. It doesn't have to pay anything to go there. Then we say like, oh, what's the best parent for the next? We check against this number and against best parent in the previous, and we find out that 3 is indeed the best parent because it's better than 1. Okay, so we got like here, and we look at this. We check the best parent in the previous, in the prefix, against this. We say like, well, it's actually a tie. Yeah, but we can say like 3 has it, right? Doesn't matter what we decide in this case. And we go here, it's still 3, so here, and here we wait a second, like 6 is cooler or better than 3. So 6 get this, and 6 also get this. Now, as you can see, it's wrong at the minute, because we only found for each vertex of the next row what's the best parent on the prefix. Now we do the same thing in the reverse order. We find best parent on the suffix, and essentially the best parent is the best of these 2. So that's exactly what I did. I didn't realize that I have to like explicitly separate these 2 passes, but it's true. So I guess something like this works. I can publish the code on GitHub if it's necessary, but yeah, let me know in the comments if it's necessary. I guess it was all for today. This video obviously will be in like chats of binarysearch.com. I'm not sure, but yeah, well, I will try not to spam it because I value your time, guys. I don't want to spam a lot, but I feel like it was a useful explanation. So let me go to the video processing, and not much editing, but yeah. I guess that's all I wanted to say for today. I hope you enjoyed. I hope it was helpful. Have a great, whatever you have now, like day, evening, morning, and see you in the next one.